Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliott Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your red shifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by Pic Astro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts.
So, Ro, today we're talking about neutron stars and pulsars.
Yes, we are. How exciting.
So, why don't you start us off by telling us what exactly is a neutron star? Does it just do what it says on the tin?
Yeah, kind of. So they are, if you think of a massive, supergiant star that's gone supernova.
Okay.
And then you're left with a collapsed core of a star. And some other stuff, but we only care about that.
Okay.
The collapsed core is a neutron star. So the stars that we're talking about before they go supernova are about 10 to 25 times the mass of the sun.
Oh,
so very big stars.
Yeah.
And then as they collapse, conservation of angular momentum makes them spin very quickly.
Okay, because again, it's getting smaller.
It's getting smaller.
So it's having to speed up.
So if you think of, an ice skater, the classic example.
Yeah.
If they are spinning around
Mm-hmm.
and then they pull their arms in towards themselves, they start to spin faster.
Yes, that's very sort of Winter Olympics.
Yeah.
Yeah, the figure skating people. Or what I was thinking of was slightly less elegant of you're spinning around on an office chair and then you pull your hands in and you speed up, put them out, you slow down.
Yeah. Less elegant, but more perhaps tangible to most people's life experiences.
To most people, figure skaters might disagree, but
yeah. Or now they have these things in parks, which I don't remember we had as we were kids, but now that I visit parks again with a toddler, they have a similar thing. It's like this weird thing that you stand on and it spins round, and you kind of hold on to it, and then you have to pull yourself in towards it.
Oh yes,
to speed up. Yeah. Conservation of angular momentum.
Right. Yeah.
So that happens, and the star collapses and it starts to spin very, very quickly. So yeah, they're made mostly of neutrons.
Okay, makes sense.
So they're called neutron stars. And they're incredibly dense.
How dense are we talking?
They're the most dense stellar object in the universe. So, excluding black holes.
Right.
And some other theoretical objects. They're incredibly dense.
So when you say a stellar object, is that kind of like a star but not a star? Or is that it's a star? Do you know what I mean?
Yeah, that's me just covering my back.
Okay.
So, we might say a neutron star is a star. We've given it that in its name.
Yeah, that helps.
But in other senses, it's not a full star.
Mm-hmm.
It's because it's the collapsed middle bit of a star, if you see what I mean.
Yes.
So a stellar object is a term that I, and I'm sure many other people, would use to describe things that are Stars in a broad sense.
Yeah, okay, stars and star-adjacent objects,
Yes.
as it were.
So, that could include the sun, a neutron star, a brown dwarf.
Mm.
You might have some, debate about whether or not that's a star, but it's a stellar object for sure.
So is a black hole a stellar object? Because, if it's like the core of a star that's exploded or whatever, that turned into a neutron star, isn't that kind of like how a black hole happens?
Yeah, I mean, there are various different types of black hole out there in the universe, so I personally would probably not classify that as a stellar object.
Okay. But you talk to black hole people...
If you're talking about a black hole that specifically has formed from a supernova, which happens if you have a bigger star than
it's even
the
bigger
10
than
to 25 solar masses that we just talked about,
right.
then I suppose in some sense you could call it a stellar object, I suppose. Yeah.
But regardless, it's pretty darn dense. So a giant, but not the biggest stars in the universe, but some really big stars. They explode, you're left with a core. The core then collapses, and as it collapses, it gets faster and faster and faster.
Yeah.
And we're just left with neutrons.
Pretty much just neutrons. Pretty much.
So how big are these things then?
Quite small.
Right, okay.
So we started with 10 to 25 solar masses, and by the time, it's collapsed down and you've only got the neutron star left, we're talking about something that, has like a similar mass to the sun, maybe like up to like 1.4 solar masses.
Right.
But they only have a radius of about 10 kilometres. That's about 6 miles.
10 kilometres?
Yes.
Okay. That's a bit smaller than the radius of the sun.
Uh-huh.
So, we've talked before about...
Which is, I think, the order of 10 to the 8 metres, as opposed to 10 to the 3 here.
Yes. So, yeah, we talked about before how the sun is basically the entirety of the mass in our solar system.
Yeah.
And it's also massive in comparison to all of the planets.
Yes.
And so we're talking about a similar sort of mass to the sun, i.e. basically our solar system, shoved into, like, I don't know, if people at home think about what's 10 kilometres away from them, then it's like that sort of size.
I mean, it's not far, is it? 10K?
Not that far.
That's a classic run.
Yeah, I mean, is a marathon 40k or something like that?
I don't know, it's 26 miles, isn't it?
26 miles.
I don't know what that is in kilometres.
But
a 10k, that's like a...
That's a
thing that many people do on a daily basis.
Do you call it a 6 mi? I don't know, like... I'm just going for a 6 mi jog run, you know what I mean? If you're a more imperial person.
I don't really know who. I don't know. Maybe.
If anyone in the States is listening and does running regularly, do they go for a 10k? Let us know. But
do you regularly run the radius of of a neutron star?
Jeez.
If so, let us know in the comments.
Jeez. Right, so that's really small. So no wonder it's dense then.
Yeah.
So
very dense. So then, if you had like a matchbox filled with neutron star.
Okay. It'd be very heavy.
Yeah. It would be about 3 billion tons.
Right. I don't suppose you know whether that's tons or tons. Is it 2 ends?
Tons with 2 ends.
So imperial tons as opposed to... I mean, that's the worst one. So I'm not sure how different they are, but yeah.
Well, I don't think at 3 billion it's going to be
very heavy.
Much of a difference.
Yeah.
Yeah.
Okay. And they are then... So it's one matchbox contains 3 billion probably imperial tons of neutrons then,
Yes, mostly.
mostly.
Yeah, so yeah, they are, to all intents and purposes, made entirely of neutrons.
Okay.
But in reality, they do have a little sprinkling of
Oh,
other things. A tiny little crust around the outside.
a garnish.
Yes, of protons and electrons and atoms.
Okay.
Just a tiny garnish, but mostly not.
Mostly neutrons.
And there are enough of them to be important.
Okay.
But
we're not calling it a proton and electron star.
yeah, but there aren't many, because most of them have most of the protons and the electrons have combined together.
Jeez.
And formed into neutrons.
When your atoms start doing that, you've got issues.
Yeah.
So is that like it's super high pressure?
So the pressure inside them obviously is immense.
Yeah, I guess 3 billion tons in a
3 billion tons per matchbox. So, you know, at the surface they're not under that pressure because the gravitational force isn't. They've got nothing above them. You know, they're just like. But once you get below that kind of surface, below that crust, it's pressure goes up very quickly.
Yeah. I guess a bit like the Earth.
Yeah.
We're not molten.
Yeah, exactly. But take that to the extreme.
Yeah, very extreme. Okay. So are there lots of neutron stars? Are we, is every second star a neutron star? Or are they quite rare events?
Not every second star.
Every
so
third.
I think we talked in a previous episode about how common certain stars are, I think. And lower mass stars in general are more common.
Yes.
To make a neutron star, you needed to start with a big, massive star. So they're not like the most common star in the universe or anything.
Right.
But there are thought to be about 1 billion neutron stars in our Milky Way.
Okay, yeah.
It's not as if there are none of them.
Yeah, it's like there are an awful lot of stars in the Milky Way, or stellar objects, and so they're not that common. But because there are so many of them, there are lots of them.
Yeah. I think a minimum estimate for how many there are in the Milky Way is about several 100 million.
Okay.
Which is an estimate that comes from, working out the number of stars that have had to go through these supernova explosions.
Right, okay. Yeah.
And being the right mass to start with to make a neutron star and not a black hole. So like big but not too big. Kind of Goldilocks-y. Yes.
Yeah.
Exactly, yeah.
And
not
then,
too big, but big enough. So
in the future there will be more neutron stars as well, because we're kind of limited in a way, like in time. If you know what I mean, there'll be some.
Yes, so that is true of a lot of astronomy. That I think it's quite normal, and I find myself being caught out by this quite a lot in seminars or talks at conferences or reading research papers or whatever. And I don't think I'm alone. I hope I'm not alone, but I don't think I am. That we kind of can quite naturally, as we're humans, not necessarily like expect that the universe is constant, but like we kind of think that our experience of certain bits of it are kind of always the case. Like, we know that the universe has evolved, but we kind of can't get our human heads around sometimes that how much that can change things, kind of.
Yeah.
So the distribution of masses of stars that form now is not necessarily the same
Yes.
as at the beginning of the universe.
Yes.
You know, so earlier on, if there's more matter nearby, around a certain place, you're going to be able to form more massive stars, right?
Yeah.
And then if you think later on in the universe and everything is much further apart, then you're trying to form stars, then you're not necessarily making as massive stars as you were making before.
Yeah. And if you've got stars that are forming out of the remains of previous stars, like the sun, right? Then some of that mass has already disappeared in some way.
Yeah.
So, yeah, you just
Maybe not
recycle them.
disappeared. Mass doesn't disappear.
No, but, you know.
Yeah, I know what you mean. So,
Yeah.
yes, we will be making more, but presumably it's going to be more and more difficult to produce.
Yeah.
I mean, you know, 10 to 25 solar masses is big, but it's not completely ginormous.
Yes.
So it's not, you know, it's perfectly reasonable to think that they're going to be being produced for a lot longer.
What's also weird with the time thing, and I know this is not exactly like revolutionary, we are sitting on a rock going around a star, and all of the stars that we can see are varying. It's not even like different ages, it's just that there's different amount of lag between each thing. And, you know, we say like, oh, the light from that star is how many thousands of years old or whatever, but it's just sort of, it's kind of weird. It's also weird that we are sort of in the exact place where we are unique in the universe as seeing those stars at that time. Do you know what I mean?
Yeah.
Which,
yeah. Looking out into the universe in general is crazy, I think. Like you say, it kind of plays with our mind a bit.
Yeah.
Even when we understand something, I don't know about you, but I find this, like, there can be a disconnect kind of between my brain and, I want to say my heart, but obviously that's not scientific.
Yeah.
But kind of my feelings and my thoughts can be quite disconnected sometimes.
Kind of like an intuition thing.
Yeah.
Or lack thereof.
So I know, I know full well that, looking into space, the further into space you look, you're looking further back in time.
Yeah.
Right? Because if you're able to see things that are further away, it's taken longer for the light to get to you. And therefore, in that sense, you're looking back in time to what that thing used to be like.
Yeah.
And things that are closer to you, that effect is smaller, so they're more recent. I know that, and that's not weird, and that makes complete sense. But then my feelings sometimes feel like, that is wild.
Yeah.
Like, that's like crazy and like weird, and like things further away are back in time. What? And they just are disconnected because it's not at all weird, right?
Yeah.
Then that like part of my brain comes back and it's like, that's not weird at all. That's just how that works. That's logic. And then my feelings are like, but that's crazy.
And it's
yeah. Like, why? It's like I feel like I have two personalities going on.
Yeah, I remember seeing once an animation type thing, animation of Orion, the stars in Orion. Like, we see it, it's sort of hourglass shaped, but then this animation was then, it sort of did a sort of side view. It moved away from the viewpoint of the Earth, and you started to see how they were related in terms of distance. Some are much further away than others.
Yeah.
And then it's just kind of weird that, like, when we talk about Betelgeuse exploding, potentially, maybe those other stars within Orion have already seen that happen. But they all are, like, they're all in the same area, so it's kind of weird that they're
Yeah.
I mean, it's also really not weird because
Yeah.
that's not how space works. But
Yeah, that's
it's
another
just-
really good example of the thought-feeling disconnect there. Because your brain, I don't know, you're like, yeah, it's a two-dimensional projection of what is really going on, yes.
Yeah.
And then your feelings are like, but what?
Yeah.
Like, that's weird. And then, like you say, maybe they've already seen it explode and we haven't yet. And like, how crazy is that? And your brain is like, again, that is a two-dimensional projection
Yeah.
effect. That is not weird.
Not weird.
Yeah,
Not weird.
but it is weird.
but it is weird. So when you were talking before about, you know, we talked about how sort of the distribution of stars and such like in the universe as we understand it. I remember we talked about, I don't know if that was the stellar classification episode, but I remember us talking, or you saying about we have difficulty seeing certain types of stars.
Yeah.
And so then, you know, maybe there are like 50,000 of these stars that we find it really difficult to discover, but we've only seen one because it's difficult to find.
Yeah.
Or maybe there's only one because there's only one. Are neutron stars difficult to see?
Yeah, they don't really emit much light because, you know, because of what they are, the remains of a star, there's no longer any, you know, fusion going on.
Right, yeah.
So there's not much light being emitted, which makes them quite difficult to find because most things in the universe we find by looking at light.
Yes.
So if there isn't much light, you're kind of in trouble, really. That being said, pulsars,
Okay.
which are a type of neutron star, are some neutron stars that are much more easy to find by comparison to other ones. Also, you can find neutron stars if they're, you know, part of a binary system. So if there's two stars,
Right, okay.
it can kind of help you to see the neutron star.
Is that in a similar way to the exoplanets thing of like it can either go past it or alter its, like do sort of weird gravitational lensy things, all of that?
Yeah,
It's
all
just
of that.
really dense and...
All of that. It's easier to see if there is another object that emits light because either that object is influenced in some way, whether that's, you know, its gravity or the, like you say, it's light being suddenly you're getting a dip in the light and you think, oh, why has it gone dark all of a sudden?
I guess it's more difficult when it's when it's like 20 kilometres across, going in front of a star that's maybe not blocking so much light.
Yeah, it's going to be dependent on the other star in the system for sure. Because if you think about it, it's about the area relative to the star. So if you have quite a big star and your neutron star is tiny, obviously, then it's not blocking that much light. If you got a much smaller star, it might be noticeable, depending. Or, like you say, kind of watching for a wobble or whatever.
Okay. Yes, I remember the watch for the wobble one. That one was...
Yeah.
That's fine.
Also, I don't know if it specifically works for neutron stars, but sometimes in a kind of opposite way to transit method where something goes in front of something and makes it look darker. You know, you can also sometimes have your object being illuminated.
Right, okay. So like light that would otherwise not be heading towards us, the observer, gets bounced off the celestial body.
That can also be a way of finding objects, and I don't know, may very well work for neutron stars in some way, potentially.
So pulsars, I'm vaguely aware of, I didn't know that they were neutron stars, but they pulse, right? That's their thing.
Yeah.
So
That's where they get their name from. They're neutron stars that have very, very strong magnetic fields.
Okay.
And because of this, they emit, you know, big beams of light out of the poles, the magnetic poles.
Magnetic poles, okay.
of the star. So you get two kind of jets, one out of the North Pole and one out of the South Pole.
Nice.
And if you are, lucky that you're able to see one of the poles, then you will see it flashing. Like a kind of lighthouse.
That's because the pole isn't always directly towards us.
Yeah, exactly. It's moving.
The magnetic pole is not the same as the rotational pole. It's off it a bit at least. So then when it goes round the rotational axis, the pole goes sort of, like you say, like a lighthouse. It goes.
You're not looking directly into where the light is coming from. You're looking in an angle. So that means that the beam of light moves relative to you.
Yes.
Sometimes you don't see it and sometimes you do see it. And it creates a lighthouse kind of effect where you see this beam flashing, every so often. And every so often is, in fact, very frequently.
Right, okay.
Because it's dependent on the rotation of the star, right? And these stars rotate really, really, really quickly.
And that's because they've shrunk down and we're conserving angular momentum, which seems to be the first rule of everything astronomy.
Oh, yes. Yes, it is.
Okay.
So, you see these very rapid pulses.
So it's less like whom, and more like...
Yeah, think like milliseconds.
Right, okay. I don't think I can do milliseconds.
No, I don't think you can. Yeah.
So why are they magnetic then? If they're just like, well, I guess you said they weren't just neutrons. Is that the answer?
Yeah.
Okay.
So they are mostly neutrons, but they have that shell that we talked about, where neutrons alone can't exist. They can't be stable. So you still have the protons and the electrons.
Yeah. And charged particles, the acceleration, which can also include changing direction, as it were.
The movement
yes.
of charged particles generates an electric field.
Yes.
Because electric and magnetic fields are
related.
I was going to say inextricably, but that's not really true, is it? are just mind-bogglingly related to each other.
Yeah. I just ask because neutrons are neutral, kind of by their name.
Yes.
So
neutrons alone aren't going to make you a magnetic field.
Yeah.
But like you say, they have some charged particles that aren't neutral. But, why their magnetic fields are as strong as they are, we don't know.
Okay.
They have incredibly strong magnetic fields. Like, crazily strong.
The Earth's one's pretty piddly, isn't it?
Yes. It's tiny.
I remember, because I've done stuff with basically MRI machines, but not MRI machines, in chemistry, and it's like the magnetic field strength of this instrument is far greater than the magnetic field strength of the Earth.
I know, whenever I see that, I'm like, yes. I feel like that's meant to be impressive.
I just find it crazy. Like it's an entire planet. I know that's not how it works, but
and again, it's the mind feelings thing, right? The thoughts feelings thing, and I feel like that's why they always give that example, because they know that it plays to people's feelings.
Yeah.
But every time I see it, my mind's like, yes, because the Earth doesn't really have a strong magnetic field at all. Is that supposed to impress me? We have something that's stronger than a weak thing.
Yeah.
Right. Okay.
Yeah. Fair.
But yeah, we don't know why they're so strong. There have been suggestions that it could be to do with flux conservation. So
sounds like a medical thing.
magnetic flux is like the amount of magnetic field, kind of,
Okay.
that you have. And if you think of the star before, it had a certain amount of magnetic field, and then you know, if you think of like drawing the magnetic field as lines,
Yeah. Okay.
um,
Like bar
and you've
magnet.
got quite a large star, you've got quite a large circle, and you've drawn some lines in it, and then, oh, your star has collapsed, it's turned into a neutron star, so now your circle has got smaller, but all of those lines of magnetic field have to stay within your star.
Right.
So suddenly all of those lines are
They're
a
now
lot closer to each
together.
other, and that
Right.
means that your magnetic field is stronger.
Right. Because the closeness of fields is kind of like the magnetic field strength.
Yeah.
If you've got a weak one, you draw like one line. If you've got a strong one, you draw 50 lines.
Yeah.
Kind of like a gradient, I guess.
Yeah. It's
cartography.
exactly the same as what you're hopefully used to see on maps. If you think of like OS maps, and they
Ordnance
draw.
Survey.
Yes.
I don't know if is that just a British? Is that the
I don't
British
know.
name for the thing? I don't know. In America, did they
Well-
have the National Geographic Society or something? I don't know.
I don't know.
I don't know.
Hopefully our listeners will tell us.
Yeah.
But yeah, if you think of maps of the geography and geology of your local area, they always will draw contours
Yeah.
on mountains, or any good map will anyway. And if you have lots of lines, you know, your contours are very close together, and that means you're gonna have to climb really hard there because that's steep.
Yeah.
Whereas if they're further apart from each other, then you're thinking, great, this is a nice easy hill to climb up. It's a shallow hill, it's not a steep hill. It's the same idea, but for a magnetic field.
I remember having weird difficulties with the concept of gradients on those kind of contours, like in high school. I don't really know why. Just didn't like it as a concept. it didn't mesh with my brain.
Oh dear.
So that's pulsars. You said that was a type of neutron star,
Yes.
pulsing. So are there any other special kinds? Or can we just say neutron stars and pulsars?
Yeah, you can get magnetars, which are neutron stars that have extremely, extremely, extremely strong magnetic fields.
So this is strong for something with a strong magnetic field.
Exactly.
Okay.
Yeah. And we're going to call it a magnetar because magnets.
Sounds like a Pokemon.
It probably is a Pokemon, or it should be by now.
What's the round ball thing with the traditional curvy magnets sticking outside? Is that a magnetar? No, that's the name of
I was
stuff.
going to say magneton. Anyway, magnetars have very strong, like crazy strong magnetic fields. And therefore they emit a lot of light, and it's very high energy.
Oh, okay.
So lots of X-rays and gamma rays with magnetars.
Okay.
But weirdly, they have slower rotation. I mean, still fast,
Right.
but slower than
Slower than, say,
other
pulsars
ones.
or
Yeah,
normal neutron stars.
which I find pretty weird.
Right, yeah.
Personally, I find that weird. And yeah, we found about 30, so not very many of them.
Right, so I guess we don't know a huge amount about them then, to some extent.
Yeah, not really. I feel like that can be said about neutron stars in general.
Yeah, okay, yeah.
But
and I guess
yes,
there
even
is,
less so about a specific branch of them.
yeah, if it's difficult to find them in the first place, but then maybe not so much with pulsars, then...
Yeah.
So is it like you've got a neutron star and it's either a pulsar or a magnetar, or is it like you've got a...
No, you can also get magnetar pulsars.
Right, okay, great.
But they're very rare, or at least they are in our data set right now.
Right,
anyway.
okay, as far as we know.
Yeah, I think I don't know, because this is not my like expertise, but I've always kind of felt like this whole area is a bit of a minefield.
Right. I feel it sounds a lot
know,
like it's coming down to
like-
trying to put things into boxes, and we're not.
Yeah,
Again,
I feel like that. It feels like a
categorising.
lot of it is like that, is us trying to understand with limited information to go by, really, and therefore trying to box things and classify things to understand. And I do wonder, in the future, are we going to look back and be like, these boxes that we made sense at the time, but they don't really make sense now? And
Yeah.
I don't know.
I mean, I appreciate it's not your field, but when you say that like magnetars are slower than other things, but we only know about 30 of them, it almost feels like you could say, oh well, they've got a really strong magnetic field, therefore they're slow, or they're slow, so they make a really strong magnetic field, and then you could imagine a sort of, well, if it's like above like this magnetic field strength, it becomes a magnetar, and therefore it's slow. Do you know what I mean? Like, you could start having arbitrary cut-off points to this is a magnetar or not.
Into certain boxes, yeah.
And then you find out, apart from that one, which crosses the threshold, but is actually not a magnetar because it doesn't do some of the things that we wanted to, or whatever.
Yeah. At which point you need to start questioning if your boxes are the most sensible way of doing things or not.
Yeah.
I do wonder in the future how many of these terms will end up outdated because they've had to be replaced or merged or something.
Or we discover a super magnetar.
I mean, it doesn't necessarily mean that it's not a sensible way of classifying things. It's just that it's not always... you can classify things however you want, and something that fits one purpose doesn't necessarily fit other purposes.
Yeah, and the purpose you have originally can be irrelevant.
Yes, exactly.
How long later? And then you need somebody like Annie Jump Cannon to come along and
sort you out.
Sort you out.
It's just, it feels a lot that we don't understand yet, which is exciting. But it does make some things difficult.
Yeah, I guess we're not really that used to... I feel like, as somebody that doesn't really know that much or really anything about black holes, for instance, kind of get the impression that, there are people with theories and such like, but you don't really know what's going on inside the black hole, right? That's kind of the point, because nothing comes out. No information comes out. So it's hard to understand what's going on inside it, because we have no idea. And, like, the idea of something like a super dense amount of neutrons is so removed from anything that we could ever possibly engage with or study on Earth.
Yeah.
Presumably, I mean, you were saying the sun is weird enough, right? Like with the coronal heating problem that we talked about in our sun episodes. And that's just there. It's very close, and we don't understand what's going on. And this is then like an order of magnitude of strangeness different.
Yeah. Yeah, it starts to cross fields a lot when you start to do this kind of research.
Right, yeah.
It's no longer... And that's something I love about astrophysics personally, is that it's taking science and applying it to a weird situation. And by weird, I just mean something that, it's removed from our experiences, really. Because we can never really go to any of these things. Like, okay, if you study the moon, right, there is a chance that you could go to the moon, right? Okay. If you study Mars, then I suppose there is a chance that you might be able to go to Mars.
Yeah.
Beyond that, that ain't happening.
Yeah.
You're never going to be going to the environment that you study. And neither is anyone else. Or at least not during your lifetime.
Yeah.
And in some cases, never ever going to that environment. And so you end up, you use a lot of science. You have to obviously the science that you use is in your work life is very niche because it's a very specific situation, but you kind of, you might be a chemist, you might be a mathematician, you might be, a quantum physicist. All of those skills and all of those aspects of science are important because a lot of the environments that you work on are so removed from what you would ever experience.
Yeah.
That you really need to have like quite weird knowledge sometimes.
Yeah.
Or at least a collaborator that has that weird knowledge, It's just interesting because a lot of stuff that I learnt in chemistry or in atomic physics or something, or nuclear physics or particle physics, it comes back because you have to understand an environment that, like you say, is very, very different.
Yeah.
Until we understood how protons could turn into neutrons and vice versa.
Yeah.
Being able to describe a neutron star was impossible.
Because, well, we didn't, yeah.
Like, I'm aware that in this case, we were lucky that our knowledge followed chronologically.
Yes.
But that's not always the case.
Yeah, and, like there would be a point where we didn't know that neutrons existed, so how could we know about stars made of neutrons?
Mm-hmm.
Or stellar objects. So.
Because, even take that, where in your everyday life do you experience something made only of neutrons? So how would you know that a neutron existed?
Yeah.
It
took long enough for atoms to be accepted in the grand scheme of things.
Yeah,
so,
that's true.
And we can now see them, so,
How times have changed.
How times have changed. Yeah, I guess it's kind of a bit like sci-fi in reverse, because I feel like you've always said to me with sci-fi, or good sci-fi, as you put it, is somebody's had an idea of like, oh, wouldn't it be cool if there was a planet, but it had a stellar core in its middle. I've got literally no idea, but you know what I mean. Like that somebody comes up with some kind of thing, some sort of science thought, and then makes a plot about it, as it were, or some kind of world situation. And I guess in this case, it's like you're given this like weird thing, and then you've got to sort of find the underlying science from it. Do you know what I mean? That would then generate that weird world.
Yeah, which feels like that kind of used to be how astronomy worked. You would look into the universe and you would find a weird exotic object.
And
of course it was exotic, because it wasn't Earth. Yeah. And then you would explain it in some way. Whereas now, that's not really the case so much in astro. It's not so much finding particular objects or particular types of object. It still happens. Yeah, because there are always going to be interesting objects out there.
Yeah.
But not so much of a thing as it used to be, I suppose.
Yeah, I guess we kind of go, oh, it's like this kind of star, but it's weird. As opposed to like, it is an unknown celestial object kind of thing. Is that kind of what you mean?
I guess I just mean that how we extract information about the universe has changed.
Right.
And so it used to be that we would look up and see something, and it would be interesting. And we would learn about the universe through that object.
Right, yes.
And now, okay, that still happens. Sometimes you find a particularly weird, star or type of object. But most of the time, a lot of information about the universe is now gathered, understood, studied, analysed by looking at lots of objects.
Yes.
And then asking what information can we extract about the universe from this.
Yeah. And then
which is a very different way of doing science.
You get the odd story now and again that's like, JWST has now seen something which completely changes astronomers' views of everything, because we used to think that it could only go up to 10, but it turns out we saw something that went up to 11.
Yeah.
Kind of thing. It's like, that's not quite the same as, like, didn't know that could exist.
Yes.
So, do they ever have planets? You've mentioned, like, potential binary systems. Is that quite common? Or...
Yeah, I mean, it's not uncommon for stars to have binaries.
And it's no different for neutron stars, because they come from stars.
Yeah.
Fair.
Yeah. So you can have binaries. You can have binaries of neutron stars.
Okay, two stars that have died.
Yeah, so that's a thing.
Okay.
Einstein predicted that such an event would make gravitational waves. Lo and behold,
They
did.
That's why you can't touch Einstein. He's a prophet of science.
Except he maybe stole most of his work from his wife. Yeah, so the first evidence of them came from 1974.
Okay.
And some scientists were looking at some neutron stars in a binary, and they were looking at their X-rays that are emitted, and they found that the intensity of X-rays was decreasing. So it was experiencing some sort of energy loss because there was less energy coming as X-rays than there should have been.
Right, okay. And that was then... this must be gravitational waves happening.
Yeah.
Okay.
So...
Because I
it's like didn't see, like, gravitational waves.
Right.
They didn't, like, look and go, oh, I can see a gravitational wave.
Because I was going to say, I thought that LIGO was, like, the first time that there was evidence of gravitational waves. But that was the first time we saw gravitational
so
waves.
LIGO gave us the first direct evidence 41 years later.
Jeez, okay. I guess that also makes sense, because somebody's had to write the what you call it? They've had to submit a proposal saying we'd like a really big, like... In fact, isn't LIGO like 2 different places or something?
Yeah.
And, and we're just going to have it on all the time in the hope that we pick up a gravitational wave. And that makes a lot more sense if they already kind of know that it happens.
Also, I guess they can write Einstein said so, and they're probably going to get some funding.
Right, yeah.
Let's be honest. I'm not saying that that's, like, legit, but...
Yes.
It probably holds some weight.
There's somebody out there that wrote the proposal and was like, damn. Like,
they'll listen to this podcast and they're like, oh, I should have said Einstein said so. We could have got that 41 years earlier.
Or maybe they're like, that's exactly what I said. When I put that in, they gave me the money.
Oh, dear. Yeah.
There's an art to writing proposals, isn't there?
There is. Yes, that is true.
Okay.
So, yes, LIGO observed gravitational waves directly the first time.
So LIGO got the Nobel Prize relatively recently.
2017.
But these other people, they'd already discovered it, as it were. Did they get Nobel Prize?
In 1994.
Okay.
Yeah, I mean, they did, I guess, discover it.
Right, yeah. I guess also...
But so did Einstein, in a way, when he predicted it.
And he only got 2 Nobel Prizes.
It mathematically. Like, discoveries aren't the kind of binary that we make them out to be.
Nice.
There are steps involved in making discoveries.
Higgs got a Nobel Prize for the Higgs boson. Did also people discovering the Higgs boson, did they also share?
Yes, I think it went to CERN, didn't it?
Classic.
Massive
team of international scientists and one guy shared equally.
I don't know. It was a long time ago. We were young undergrads at the time.
Yeah.
sitting in the physics cafe
Yeah.
when the news came out. Weird how that's one of the things that I remember in life. Because, you know, I was interested,
Mm.
you know, and I was very interested in particle physics when I was a teenager, before I went to university. So I was interested. But I don't feel that by the time of the Nobel Prize, Peter Higgs winning the Nobel Prize really was like that significant a life event for me.
Right, yes.
And yet somehow, it's one of those weird things that I can remember where I was. I can remember sitting there
Yeah.
when the news came out, you know.
Yeah. It's like when you...
Like, why is that something I can remember? That's really bizarre.
It's generally like, you know, I can remember where I was when Nelson Mandela died.
Yeah.
Or, I guess, when his death was announced.
Yes.
Margaret
Thatcher, I remember that one.
I don't remember that one.
I remember that one. Loads of other
Terry
political
Pratchett.
leaders.
I remember Terry Pratchett.
Yeah. Oh, Terry, R.I.P. You live on in our hearts.
But in this case, it's Peter Higgs actually not dying, but
Yeah,
getting a Nobel Prize. So pretty good.
It's
You've made it onto the list of events that are memorable, but are not tragic.
I guess because often it's something that's shocking in some way.
Yes, that's true.
You know, but I didn't feel that was particularly shocking either. So I don't know why.
I don't know.
If anything, it felt predictable, really.
Well, he predicted it. Well, not the Nobel Prize, but I guess. But
yeah, strange times.
Strange times.
So yes, they can be binaries of neutron stars.
So can they also have planets?
They can. Yeah.
Nice.
You're gonna like this one.
Okay.
There's one neutron star.
Okay.
It's got 3 exoplanets that we know of.
Not too shoddy.
Yep, they've all got names.
Of course they do.
Yeah.
Is it X47?
And I was going to say, and it's not a number plate.
Nice.
Yeah. The first one's called Draugr.
Like in Skyrim?
Like in Skyrim.
Or Norse mythology?
Yeah.
Nice.
The second one's called Poltergeist.
Okay, interesting. I'm seeing a theme.
Yep. Which I think is the most famous one of the lot. And it's definitely the one that I remember. Though I couldn't tell you why. Don't know what's special about Poltergeist. Or rather, I don't know what's particularly special about Poltergeist. The third one's called Phobetal.
I've got no idea what that... I'm going to guess
I
that's
don't know what that means.
I'm going to guess a Greek god.
Yeah, it's got Phobos vibes.
Mm.
But it's obviously not Phobos. So...
That's, the moon of... One of the moons of Mars, which is... Fear? Is it? Like a phobia?
Mm.
Is it fear and... No, it's not
Deimos.
panic. Yeah, what's Deimos? Fear and loathing. Yeah.
I think it is, but I don't know. I wouldn't swear to it. My
Fair.
Greek
Yeah.
is
It's all Greek.
subpar.
All Greek to me.
But yeah, Draugr is the smallest exoplanet that's ever been discovered.
Okay. That's
Yep.
Well, next time you play Skyrim.
Just think of that tiny little exoplanet out there.
Jeez.
Yeah, imagine being an exoplanet around there.
Because
Because presumably you're there before it goes supernova.
presumably.
And
Because you could maybe fall into it or something.
yeah, fried.
Jeez.
So yeah. But even ignoring the fact that you've had to live through a supernova.
Which is not the greatest event to live through, you wouldn't have thought. Or not one that you would live through, I guess.
Not ideal. You've still got really high magnetic field strengths around your neutron star.
Right, yeah.
And lots of radiation as well.
Yeah, so not
So
really...
you're still getting bombarded with radiation. If you're a planet, or indeed another star.
Okay, yeah.
So yeah, you're not going to have an atmosphere if you're a planet. But again, you probably would have lost that when it went supernova anyway.
Fair.
So maybe you're not too worried about that. Maybe you're like, well, it couldn't get any worse.
Yeah.
Who knows?
So we're not not sure why we'd want to, but we're not going to move to an exoplanet around.
Probably not to Draugr or Poltergeist or Phobator anytime soon.
No.
Speaking of stellar objects, if you had been a happy little star with a 10 to 25 solar mass neighbour in your binary.
Yeah, and you're getting along just fine.
You're getting along just fine, then for some reason it goes absolutely berserk, goes supernova on you.
All right, yeah, midlife crisis.
You're probably going
End of
to
life crisis.
end up as a stellar object. Because you're probably going to have a lot of yourself
Oh, ripped off you.
ripped off as it goes
Jeez.
supernova. And so you might not be a star by the end of it.
Jeez.
What
Is that then? You're like a brown dwarf, or are you like are you a planet? Who
knows? You're a stellar remnant,
You just.
but who knows exactly how? And again, the magnetic fields and radiation of a neutron star are also going to rip bits off the other star in the binary as well, even if it has survived to some extent the supernova. So, not ideal places to live.
Not ideal. Well. So, when did we find out about neutron stars existing? Was that like?
Well, the first neutron stars detected were pulsars.
Because they're
Because
pulsing.
they're easier
So we
to see.
got you.
By
Jocelyn Bell.
yes, indeed. Dame Jocelyn Burnell Bell.
Oh, sorry, Dame.
She's a dame now.
Dame. Like Helen Mirren and other people that are dames. Judi Dench.
In
Run out
good
of dames.
company, the three there.
Kelly Helms?
Is she a sports person?
Yeah, didn't she run?
I was going to guess runner, but I didn't want to show up my lack of sports knowledge.
Yeah, sports. I'm not going to win the sports round, did the...
No. You do surprisingly good at it. I don't know how, because sports aren't your thing.
Generally, you kick a ball. Not in athletics most of the time, but a lot of other ones involves that.
So yes, Jocelyn Bell.
You've seen Jocelyn Bell.
I have, yes. Yes. She said hi to him.
It was like, she just like walked on the street, she was like, hi.
No, I went to a talk that she is given. Took the, at the time, baby. Yeah, so they've seen her too.
Did you do that thing and like, kiss my baby?
No, I didn't.
I don't know why people do that, that's so weird.
It's so weird on so many levels. No, yeah, it was good. I'd definitely go to other talks by her and, meet her. If I got the opportunity to meet her again, I definitely would. Very, very interesting person. Has a lot of cool stuff to say about lots of things, really, not just physics, but lots of cool stuff to say about physics. And very, a very important activist as well for making physics more, diverse and helping people into physics careers that maybe wouldn't be encouraged to or wouldn't be able to otherwise. So, very important work that we should all be really grateful for as well. But she's done a great deal of good for the world in many ways. She hasn't always had the easiest life.
Okay.
And she's quite famous for...
Not getting a Nobel Prize.
Exactly, yes.
I also have not got a Nobel Prize.
Yeah, but you haven't done anything worthy of getting a Nobel Prize.
Okay, yeah. I'm also not famous for not getting a Nobel Prize. I'm just not famous for getting a Nobel Prize.
Whereas Lee is famous for not getting a Nobel Prize.
Right.
Yes. Her, at the time, PhD supervisor.
He gets...
Yes.
I
was debating whether or not I should give his name for,
Well, people can look it up, so...
I know, but I'm like, do I really want to add him into the history books? Do you know what I mean?
Okay, did he do a bad thing? Or not?
Yeah, he took the credit for it.
Okay.
And she's always been very, I don't know if graceful is the right word, but, she has commented before, like, oh, I was only a PhD student, basically, and Nobel Prizes shouldn't go to PhD students, Very, I don't know what the word is.
Self-something.
Yes.
What's the word? Sort of humble, I guess?
Yeah, I suppose. Anyway, so, it's right that he got it, but it's not because she did the work. She made the discovery. She should have got the Nobel Prize. And she didn't. He got the Nobel Prize in 1974 for the work that she did in 1967.
Right.
And it creates a lot of emotion for a lot of people, I think, within astrophysics and outside of astrophysics, people who care about science, whatever.
Yeah.
Because there's a lot of, bias, lots of racism and sexism and everything that goes on within science anyway, but also very much within the Nobel Prize.
Yeah.
Establishment, if you like.
Yeah.
And this, is another case of that. Because
there's
if she was a man, would she have got the Nobel Prize? Obviously, when it comes to very specific events, it's like climate change, right? Like, you can't look at a specific event and say that was caused by climate change.
Yes.
A lot of the time, you can't look at a specific event and say that specific event was definitely caused by sexism. You sometimes can.
Yeah.
But, you can't always do that. But it's not really necessarily just about specific events. It's about the culture, and it's about the situation as a whole.
You can never prove that an individual event is, or almost never, I guess. Or generally, especially as they don't generally have a record written down somewhere.
Yeah, because most of the time people haven't written down, we will not give this Nobel Prize to Jocelyn Bell because she is a woman.
Yeah, so you can't be like...
They might have said it.
This event
but they've not
was
written it down.
sexist, but you can look at the trend and be like, oh, wow.
Yes. And, she experienced a lot of sexism throughout her career. And unfortunately, it's still a thing that happens today in science, in astrophysics. Some branches more than others, but it's still rife, and it's definitely still rife within the Nobel Prize establishment.
Yeah. I mean, there was the Nobel Prize for the solution of the structure of DNA goes to Watson and Crick and somebody else, I think. And people mention that one because
they happened to find someone's notebook.
Because it just happened to fall into, very dodgy thing. Also, one of them, I can't remember which one, but one of them is very dodgy anyway and sort of eugenicsy. Don't come for me with lawyers, but anyway.
Yes, there's a lot of ethical
but
things.
But there's ethical things there anyway.
Yep.
But then Rosalind Franklin, she doesn't get a Nobel Prize, but she's dead at the time that they get the Nobel Prize. Mm-hmm. And she's done all the crystallography, which leads to the solving the structure.
Yeah,
she's basically done the structure.
In that case is, I think it's questionable that you should only give the Nobel Prize out to people who are alive. However, that is the rule. Yeah. And so the issue is not so much that she didn't get the Nobel Prize, because, like you say, unfortunately, she wasn't alive anymore. Yeah. The issue is that the history books have written her out of it incorrectly, have written them into it incorrectly, and that this idea perpetuates within society. I saw and I absolutely kid you not, this year on International Women's Day, I saw multiple, I think it was maybe 2, but it might have been 3, I wouldn't swear, different institutions talking about, because they weren't, specifically talking about International Women's Day, but they were talking about Watson and Crick discovering DNA.
Yeah.
On International Women's Day.
Nice.
I mean, you can imagine the responses to that, because the issue is that it perpetuates.
Yeah.
It has since been disproven that they, did all of this work.
Yeah.
That they found all of this, and yet it's still trying to be rewritten into the history books by people.
Yeah.
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 So yes, I think probably if you mention, pulsars, maybe not neutron stars, because maybe not everyone thinks of them as the same thing. But I think if you mention pulsars to a lot of people and you ask them, what they are or what else they think of, they might not be able to answer very much about them. They might not even be able to tell you what they are. But a lot of people could relate pulsars to Jocelyn Bell.
Which I think is a pretty good state to be in as an individual.
It's worked out better.
Yeah.
Than for a lot of other scientists in a similar situation to her.
Yeah. Also, I just remembered why I have heard of pulsars. I'm pretty sure it's in... So, I guess it's because of the rotation rate, right? They're regular.
Yeah.
Right? It's like, when you say it's like how many times a second,
clocks.
it's like, that's the thing, right? Because is there not stuff about... It's not even in sci-fi, isn't it on Voyager? It's like... Haven't they got written on the plaque that we sent out into space to say, this is where Earth is? It's like related to the positions of pulsars.
Yeah.
Because it's like aliens would be like, oh, well, that frequency matches this particular star, so it must be there. And that's like the only way that we know of, really, to have like a sort of landmarks in space, as it were.
Yeah,
that we can position things.
Like you say, they're little kind of signals, little directional signs, I feel like.
Reference points.
Yeah.
Yes.
Because they're regular and be unique compared to each other in a way, dependent on their rotation rate and how they pulse. And they're kind of constant,
Yes.
They're not like other things where events are, kind of come and go or whatever.
Like you were talking about the activity cycle of the sun before in the sun episodes. It's like it pulses and it keeps pulsing.
Yeah.
As opposed to it pulses for this period, this frequency, and then it slows down and then it speeds up. It's like it's always the same.
Yeah.
That's that.
Yeah.
So then we're back to mapping again. Talked about
mapping out the
space maps,
the universe, or at least the local space with pulsars.
Nice. Thanks, Jocelyn Bell.
Yeah.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and if you like, you can leave us a nice positive review as well. It really helps the show and it makes it easier for more people to find us.
Feel free to send us any comments, questions, or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.